இதுக்குள்ளேயும் சொன்னதே சொல்லிட்டு இருக்கா, பைத்தியக்காரி பைத்தியக்காரி.
Shall we start?
Yes, ma'am.
Let me share my screen. If the screen goes off in the middle or audio is not proper, please let me know. Okay, I hope I'm audible. Actually,
Yes.
I'm recording in another local system, but instead of this echoing, I have reduced the voice. I think it is not recording. Give me a second. Okay?
All right. Since we have seen some of the problems from week 2 and week 3 previously, today we are going to solve some problems from week 4. I hope you have gotten the practice assignment and assignment, right? It has been released?
Yes, ma'am.
Yeah, right. So we'll try to solve practice assignment 4 today. Before that, last time when I went through this lecture series of week 4, I asked you to prepare some tables for you. I hope most of you would have not created, so I thought I'll make it easy for you. So we'll make that table together. You can use it for your quiz one preparation, right? The major concepts in week 4 will cover the time domain responses and steady state error based on questions. Okay, these are all the two broader categories which covers most of the marks. So we'll try to focus on this first and then comes to the rest of the contents of the week 4. Okay, that starts in lecture 4, I guess. Right, this has this. So we'll start with. First of all, we will have to write all the formulas this side so that we will be using that for solving the problems. What are all the important formulas you would need is the first one is the rise time. We call this as TR. TR would be pi minus theta divided by omega d, where omega d is your, we already saw this well, zeta square, 1 minus zeta square. Okay, then the delay time, this is this is one. The delay time TD can be written as 1 plus 0.7 You have to memorize this formulas to solve the problems. By omega n, this is another equation we want to see. Then it is peak time, this will be pi by omega d, where omega d, what it is omega d, we can expand that. Then peak overshoot, we call it as mp percentage, that will be 100 into e power minus zeta pi by root of 1 minus zeta square overall into percentage. Okay? This we will calculate always in percentage. That's why we are multiplying into 100. Okay, this is another equation. Then settling time will be of two types. One is 4 by zeta omega n, this is for 2%. Another one is 3 by zeta omega n, this is for 5% tolerance. Okay, whatever tolerance they have asked in question, you should use the respective equation for that, formula for that. So these are all the important time response specification formulas that we will be using to solve the week 4 content. Right. The next important topic is steady state error. The steady state error, I think you would have seen the lecture, but anyway I will brief you through that. First of all, when you want to find the steady state error, let's take this is a actual set point in the sense how I want the system to behave. For example, if I turn on the fan, I would want the fan to run at 200 rpm after some times. Maybe it won't be achievable in the first few seconds, but after 3-4 seconds I will expect my fan to run at 200 rpm. So we call this as a set point, whatever way you want the system to behave. So I'm taking this as a set point, but actually your system in real time or the physical system won't be behaving in a way you want. So this might be behaving like this, or this might be behaving like this, or this, or this. So we don't know. It depends on the nature of the system. That's why we went into the control system concepts. So using some external influence or some external force, we can make the system to work like how we want it to be. So now this steady state error would reflect how you difference between how you want it to be and how it is actually. So that is the difference between this steady state, that is the steady state error. That is difference error between the actual output and the desired output. It's very simple. So how we can interpret in terms of a equation or in terms of a block diagram. This one. So if I take a control system, let's take my transfer function, I call it as g of s. Okay, my output, I'm speaking in terms of Laplace transform. So I'm giving an input that I call it as r of s, and there will be a summation point where I am considering the feedback. I'm considering one as a single or unity feedback. I'm considering for simplicity. So I'm considering a negative feedback, so there will be a minus sign here, and this input will be add on, so there will be positive sign here. How we can interpret this block diagram, the physical system, into a mathematical equation in the sense, always we represent the output, Laplace of output by Laplace of input, that is the transfer function. So if I want to represent in terms of a mathematical equation, I would take the Laplace of output divided by Laplace of input. That's what I have written here. Okay, that's what I have written here. Then the equation, I can write it in terms of, if it is a closed loop system, the formula you all know, right? G of s divided by 1 plus G. Yes, exactly. This is for negative feedback. We are not bothering about positive feedback for now. Most of the control system we will be interested will be in the negative feedback. So this is of our interest now, right? Now I'm introducing another term that I want to look for is E of S. Okay. That is, the weight is not changing. Anyway. Okay. I'm now interested in what is the error between these two. That's why we are speaking about the steady state error right now, right? So I'm very much interested in getting to know about the error, how much my system has. Now I am looking into this concept, that is E of S. If I want to write in terms of E of S, I would say E of S will be, we are adding the R of S from here and subtracting the H of S from here, right? So I can write in terms of R of S, there will be a Y of S, that H of S is in terms of Y of S, right? So I'm going to write this in terms of R of S minus Y, where Y comprises of H information indirectly, okay? Now, so this can be written as Y of S, we already know. If I take R here, R of S minus, I'm going to write this entire term with R here, right? Instead of here, I'm going to equate it to Y of S. So this will be G of S into R of S divided by 1 plus G of S into H of S. H is considered to be 1, so I'm leaving it for now. So this will be resulted in R of S will be common, so this will go here. So ultimately you will get R of S divided by 1 plus G of S. There will be H of S here. Since it is a unity, I am leaving it for now. Okay, right. So this is your error term, E of S. So this is what we are interested in right now. Now, can you recollect the final value theorem? Why do we need final value theorem? If there is some output response, after some time or after an infinite time or after some interest of time, let's say 5 minutes or 10 minutes, whatever bounded time or unbounded time, how the system behaves. If I want to know, I have to come up with the final value theorem. This final value theorem says after infinite amount of time, what will be the value of the system or what will be the output of the system. So if I want to know how this error propagates after some period of time, I will use this final value theorem for this E of S. So that I will know, okay, after some time when I turn on the fan, is it rotating at 200 or is it rotating at 190 RPM? What is the difference between this? To find that, I'm going to apply the final value theorem. Final value theorem states that if you want to find t tends to infinity, you would be using limit s tends to 0, some transfer function, whatever transfer function you want to find. Here I am interested in finding the E of S transfer function. So I'm going to use the final value theorem here. The final formula will be limit s into E of S. That's it. So E of S you already know. How can I expand this? Limit s tends to 0, s into R of S divided by 1 plus G of S. Right? Any doubt till here? Anyone has any doubt till here? Why are we doing this? What is the purpose of this? Any doubts? If you have, just raise it. Okay, good. Now, there are different standard inputs we have seen so far, right? Most of the inputs will be step, impulse, parabola, or ramp. These are all the 4 common types of control signal inputs we will be interested in. So we are going to see, whenever I am giving one input out of these combinations, how my error would be for some systems, for different systems. So we are going to see one by one. First of all, we will start with unit step because impulse doesn't matter. It will be there for only 1 second. So it doesn't matter to see how after some time how it will be, how the error will be. So we will start off with the unit step input. Right. So for a system, if this is my system G of S, closed loop system, Y of S, I'm taking a unity feedback and give it back to my system with negative feedback. Right. So here I'm interested in finding this E of S. When the R of S of this system would be 1 by S, that is step input, unit step input, how my E of S will propagate at last when t equal to infinity. Right? This is what we are going to find right now. So the formula, you know, E of SS is equal to limit
Yes tends to 0.
0. Yeah. S into what did I write? R of S divided by 1 plus G of S. Right. Okay. Now, instead of R of S, I am going to replace it with 1 by S. That's it. So S into 1 by S divided by whole by 1 plus G of S. So this S and this S will get cancelled. What I will be left with, limit S tends to 0, 1 by 1 plus G of S. Right. So this is whenever I am using R of S is equal to 1 by S, my error, steady state error will look like this. So it depends on the transfer function. Okay. We will first just highlight this and we are going to revisit this again after completing each and every input. Okay. Right. Now I am going to consider the second input. Whenever the input is unit ramp, for example, R of S is equal to 1 by S square. That is ramp. Ramp will look like this, right? Okay. This unit ramp. Okay. Somebody.
Ma'am, can you tell once why we are not considering impulse?
Oh, okay. Impulse will be available only at one point, right? At only 1 second. Whenever you are initiating that input, it will be available. After that, it won't be available. Then it doesn't make sense when you want to see after infinite time how the system will look like, right? So that impulse response is primarily used to test the strength of the system. Just for example, a lightning, how well this system is able to withstand this power. That kind of practically I'm saying that kind of test impulse will be useful. Rest of the things, unit steps input or ramp input or parabolic input will be there for a long time. Then it makes sense after some time how the output will be. When there is an input, there will be output. So the input should be forever, right? That's why we are not considering impulse but rest of the inputs. For this kind of application, impulse won't be useful. That's why we are leaving. I hope this answers your question.
Yes.
Right. Okay. Now we are considering ramp input. Similarly, what have we done before? We are going to do limit S tends to 0, S into 1 by S square. Instead of S, I am going to put 1 by S square. Then this will get cancelled. The remaining we will have S tends to 0. 1 by this S will be multiplied to both of them. So it will have S plus S into E of S. Right? Remember, this is E of SS, then R is equal to 1 by S square. Right. We'll highlight this and read it together. The third input I am going to consider is R of S is equal to 1 by S cube, that is parabolic signal. So when we just try to tell with me that this will be S tends to 0, S into 1 by S cube divided by 1 plus G, then this will become limit 1 by S square plus S square into G of S. This S and one of this S will get cancelled. Remaining S square will be there. So this is E of S and R is equal to 1 by S cube. Right. So out of these three, we will make a table here. When R equal to 1 by S, the output is limit S tends to 0. Right. I'm going to keep this S tends to limit S tends to 0 common. Okay. Just I'm going to write the rest of the thing. This will be left with 1 by 1 plus G. When R is equal to 1 by S square, this will be 1 by S plus S into G. And R is equal to 1 by S cube. This will be 1 by S square plus S square into G. Now, since the limit S tends to 0 is common, here when you put S tends to 0, it doesn't affect anything here, right? Just it will left the same thing, 1 by 1 plus G itself. Now, when you put S is equal to 0 here, it will become 1 by infinity. Am I right?
1 by 0, infinity.
Yeah, infinity. This will also be 1 by 0, infinity. Right? So, this is the type of a system where now this is a common understanding. When we are not bothered about anything about the G, right? Without considering the G, the output we are putting S is equal to 0. Let's keep this up. When the system when we are considering how the system or the transfer function will look like, this will change. For example, right now we are considering the system transfer function in terms of type of the system. You would have crossed across this concept. Type is equal to the number of poles at origin. Right. If I consider any system, if there is any pole, how many number of poles there in the origin, this directly tells the type of the system. For example, when we consider the denominator, we would call what are all the terms that is being placed in the denominator as poles, right? S of s plus a, this could be s plus b square, s square, different types of poles we have crossed. Okay. The first thing is, since we are considering only the poles at the origin, not in any other place, we are going to be interested in only S terms. So the highest degree of the S term will be the type of the system. So if there are two poles at the origin, it will be S square. If there are three poles at the origin, it will be S cube. Similarly, number of poles at the origin will be equal to the degree of that poles, and that is directly called as a type of the system. So based on this type of the system, how we are going to change this, or how this steady state error is going to change, that's what we are going to see. When the type of the system is 0, meaning there is no pole at the origin. Right? First, if I consider there is no pole at the origin, there will not be any S term here. So I will just take and put it down. And select it. For S is equal or is equal. What does that mean? No. I don't know why it's happening. Okay, let me just explain from this. Okay. When the type of the system is 1, I'm sorry for this. When R is equal to 1 by S, this will be 1 by 1 plus G, right? When R is equal to 1 by S square, this will be 1 by S plus SG. R is equal to 1 by S cube, will be 1 by S square plus square. Okay, good. Now, when the G is equal to type 0 system, type 0 system in the sense there will not be any term that has S, but there might be S plus A, S plus B, the whole square or anything, but not only S. Okay? If this like that, so when I consider there is a system that is S plus A, I'm going to take limits S tends to 0, 1 by 1 plus this kind of G I have. So when I substitute A, will this change the system to 0 or infinity?
No, ma'am.
No, because this term will not affect the system. There will be some finite number you would take. This will always be finite. So the output will be 1 by 1 plus G always, where this G we are calling it as KP, where KP is equal to G. This we are calling it as position constant. position error constant. Good. When the type is equal to Z, when the type of the system is equal to 0, or in, sorry, when the input is equal to unit step, the output or the error constant will be 1 by 1 plus B, where we call this B separately as Kp, where Kp is equal to Z. I'm going to call this as position error constant, right? For type 0 system, this will be as it is. For any type of the system, type 1 or type 2, any type of the system, this will be as it is, that we are going to see here. Right. For the same type 2 system, I'm considering the input as R equal to 1 by S square. This will be S plus S into, there will be one another term S. This is type 1 system, right? S into S plus A or something I have considered type 1 system. Now how it will be? Limit S tends to 0. So this S and this S will get cancelled and this will go to 0. Then again I will get a finite output.
Yes, ma'am.
Here is in the left hand side you would see all this. Okay. Good. I might be making some mistake, I think. For type 1 system, yeah, right. Correct. Right. For type 2 system, for type 0, I am going to see for all the input. First of all, we found the type for type 0 system, it will be 1 by G as it is. Instead of calling it as G, I am going to call this as Kp, because the G is the position constant that I defined already. Now, for we will fix type and then we will go through all the inputs, that will be easy for you. So therefore 1 by S, we found that it will be 1 by Kp, where it will be 1 by G. That's it. Where Kp is equal to G. When it is 1 by S square, we will stick for the same type 0 system. It will be 1 by S plus SG, where G is the type 0 system. There will not be any S terms to cancel this. So this will become 1 by S. I don't know. 1 by S plus S into G. This S will not get cancelled as the type of the system is 0. So this will give you 1 by 0. This will go to 0. This will go to 0. Anyway, this will go to 1 by 0. That will give you infinite. So this will be infinite always for all the system. For type 0 system, whenever you are considering the input as RAM, you will get infinity as a error, right? When you consider input as parabolic, since the ramp itself is giving infinity, parabolic is not going to make any changes since the type of the system is 0. This will also give you infinity. Any doubt till this? Anyone got confused here? Because to complete this topic, you would be confused with what is position constant, why do you call it, or what is the ESO. So many confusions will be there. So you should be very clear in. Clear?
Yes, ma'am. Yes.
When we change the type of the system to type 1. Now I'm going to go through for all the input. Now I have 1 by 1 plus G, where G has some S. This G term has some S because this is a type 1 system. Now when I put S is equal to 0, will it affect the system?
No.
Right. This will be the finite. So it will be as this. This will be some finite, where in this case this is 0, it is not infinite. So whenever this is a type 1 system, this will be 0. The error will always be 0. So you can say when you have a type 1 system, giving an input of a unit step will bring down the error to 0. Then you can conclude that the system is very good. There is no steady state error. The system is actually following the input properly. It is giving the output as expected. The actual output will be equal to the desired output. So this is considered to be a very good system. Okay. Right. When I give the input as 1 by s square, this will be s plus s into, there will be one term in the s, right, into g. Instead of g, I'm going to put one s. So this s and this s will get cancelled. When I put s is equal to 0, I will again get some finite output, right? Some finite number, not infinite. Better I will write it as finite, okay? For now, we'll come back to that. Right? We will have some finite number. So this will also be finite. Third one, when I put parabolic, here comes the problem because one term, which is a type 2 system, sorry, type 1 system, there will be one s term. Now come, there is s square here, but still it has one s. So this will not give you a finite output. So this will give you a infinite output. Right, good. So when you consider a type 2 system, similarly, let's see how well we will be able to type 2. I'm going to write. So when I consider 1 plus g, where I have 1 plus 1 by s square, right? So this doesn't affect my system. This will be 0. This will be infinity. 1 by infinity will give us 0. That is finite. Good. This will also be good. Type 2 system. This will also be good. When I consider the input as 1 by s square, s plus s into 1 by s, this s will get cancelled, and sorry, this will be s square, right? 1 s will also be there. 1 by s is equal to 0. This will be infinity. Anything by infinity will be 0. Again finite. This is also a good. When I give 1 by s is cube, this will be s square plus s square by 1 by s square. This will get cancelled. This will be 1 by infinity will give you some s square 1 by 0, 1 by 0, right? No, I'm missing something here.
1 by s cube, ma'am, because the system is.
Good, thanks. So you will have some finite value, not infinite value. So I'm going to write it as finite. Okay. Now we have this table. Okay. Here, instead of that finite, we want some solid output. So how we are going to call this as we call this G as KP, I am going to call this denominator 1 by SG as KB, 1 by S square G as KB. That's it. Nothing else. So this will be 1 by KB, this will be 1 by KA. It's very easy. Just remember the table while you are solving your problem, save your time. How you can go through this? You know how this transfer function comes. So you won't be like mud hard this. So just know the information, but keep this table in mind to solve the problem easily and within the considerable time. Right? When the input is step, type 1 system will give you finite output. This will be type 0 will give finite. Type 1 will give 0 and 0, where 0 steady state error is considered to be a good system. When the input is RAM, type 0 will give infinity, it's very bad. This is also bad. So type 1 system will give you a finite, and type 2 system will give you 0. Some finite value will give you 0. But this finite value mostly be lesser than. When the input is parabola, type 0 and type 1 will give you infinite output, and type 2 will give you a finite output. So this is how you can, so if there is a fill in the blank question. consider a control system where the control system is the type 1 system and the input is the parabola. Straight away, you can fill the answer with as infinite steady state error. That's it. Right? Otherwise, if they ask some other thing to find this finite value, we will see how we can solve those problem and find the exact numerical value for this. Now I hope you understood this concept, right? Anybody has some doubt here?
No, ma'am, understood.
Right. In the concept, you have no doubt, or if you want to ask any question, just turn on your mic and ask. We will proceed with the practice assignment questions. Question number 1 is open your system, open the practice assignment questions. The first question is a unity feedback control system forward path transfer function is given into g of s is equal to k by s into s plus 2, right? Given that the defined specification requires steady state error. So far we have seen how to solve this thing and we know the shortcut formula for this for a unit ramp system. So when you see this, you should think that this is 1 by s square. Okay. They have given the value to be 0.05. Okay, this 1 by s square will be equal to 0.05. Calculate the appropriate value for k, where k is the gain mentioned in the transfer function. This is a little indirect question. Not they haven't asked about the steady state error. They have given the steady state error and asked about some missing information from the transfer function. But anyway, we are going to solve it straight using the formula. So first of all, to solve this, you need these many information. What is the input? To solve this kind of question, you should ask yourself what is the input being given. Second is what is the type of the system. So if you know these two, you can take this table and find if you know the type and if you know the input, you will be able to solve the question using this. Right? Mostly the type will be maximum to 2. Otherwise, it will be very complicated. Right? Now, from this question, we know the input is RAM and the type of the system. How will you find? What is the type of the system?
It is first order.
It is
First order, ma'am. S
first
square.
order. Yeah, good. So type of the system is one. Type 1 system. So just look for the table. Type 1. Then it is ramp input. So they have asked for some finite value. We are going to get some finite value. This is the initial understanding we can come across. Okay, right. Now how we are going to solve this problem? First of all, E of SS will be limit S tends to 0, S into 1 by, when it is a ramp, it will be S plus S into G, right? So this here will get cancel. We have,
For ramp, S square. Ma'am.
oh, okay, sorry. So this will be limit S tends to 0, 1 by S plus SG will be left with it. So this will be limit. When s equal to 0, this will go to 0. So we will be left with s tends to 0 into s into 1 by sg, right?
No, ma'am. S square.
We can
Yes, only S. For ramp, this S square for ramp.
plus sg, then this will be limit s tends to 0, 1 by sg. Is it right? Here it is, right? Unit ramp, limit s tends to 0, 1 by s into g. Now, I am going to find 1 by s into g of s is k by s into s plus 2. I am just taking a longer route just to make you understand. There are straight away formula where you can kv equal to, you can use this formula also. S equal to 0, s into g. You will get it. But for initial people who can be a little bit difficult, I'm getting S and S will get cancelled. Remaining thing S into 1 by K into S plus 2. Right? If I put S is equal to 0, it will be 1 by K by 2, right? This will give you K by 2 as, sorry, 2 by K. 2 by K, right? The E of S will be equal to 2 by K. This is the steady state error we will get, that is, that we know is finite, right? So we know the left hand side. E of S they have given, that is 0.05. I'm going to substitute straight away. 2 by K you will get, K if I take it here, 2 by 0.05. This will give you 40. So the K will be 40. Any doubt? Any doubt so far?
No, ma'am.
Okay, good. So if they have given the K and if you have asked to find Kv or velocity constant, you have to find this step. That's it. You have to find the answer for this step and just invert it, you will get the K. Okay, we'll move forward to the second question if you don't have any. The second question says a unity feedback system has 40 a transfer function given type 40 S plus 2 divided by d of S into S plus 1 into S plus 4, where this is the type 1 system. First question is find the type of the system. Second question is all error coefficients. Position error, velocity error, and the acceleration error, that is Kp, Kb, and Ka they have. And the third question is error for ramp input with magnitude 4. It is not unity ramp, ramp input with the magnitude of 4 instead of 1. First of all, the first division of the question is straightforward. Since the denominator has one S term, the type of the system would be 1. I hope it is clear to everyone. The second question they have asked is all error coefficients we have to find. First, we will start with Kp error coefficient. Where Kp, how will we find? Here it was given, right? Just see the left hand side. Kp, Kv, and Ka. I have put it in box. Just take Kp is equal to limit S tends to 0, G of S, where G of S they have given limit S tends to 0, G of S would be 40 by 40 into S plus 2 by S into S plus 1 into S plus 4. When there will be S. No, sorry, there will not be any S for Kp. Okay. So this will be when you put S is equal to 0, you will get
40 by 4 times 2.
Kp will be infinity, right? Anything by 0, it will give you infinity. So
No, ma'am. No. Yes, ma'am. Yes, ma'am.
yeah, it will be infinity only. Kp we are finding. After that, we are going to find E of SS, that is 1 by 1 plus Kp, where you can see here 1 by 1 plus Kp when input is 1 by S for type 1 or type 0, it will be 0. So since this is 0, it is a infinity. Since it is a type 2 system, 1 by infinity would be 0 here, as we saw in the table now. Right. The second coefficient is Kv. You can solve straight away with the S into S plus G of S also. Otherwise, you can take this shortcut equation, limit S tends to 0, S into G of S, when you are asked to find the coefficient separately. Just limit same 0, S into 40, S plus 2 by S into S plus 1 into S plus 4. This S and S will get cancelled. So rest of the things would give you 40 into 2 divided by 1 into 4. This will be 20, where kV is equal to 20, ESS is equal to 1 by kV. This will be 1 by 20, 0.4 or something, right? Sorry, 0.05. The third quotient is Ka, where Ka will be here in the left hand side. It is there in the violet color box. Limit s tends to 0, s square into g of s. Instead of s, we are going to keep it s square into g of s. S plus 2 by s into s plus 1. Yeah.
Would you please share the PDF in this
Share the PDF in?
this space?
Okay, this PDF. Solve the
Uh,
PDF. Yeah, I will
yes,
share
ma'am.
it.
Thank you.
Thank you. I will share this recording and the PDF. Actually, we have shared those recordings with the office staff people. I don't know. You didn't get it yet, right?
Yes, ma'am. And one more thing, unable to access the GA solution in dashboard under supplementary content.
You couldn't access the solution.
Yes, ma'am.
In which, where, which folder or where?
Supplementary content.
Okay, I will check with them. I'm not aware of this. I will check with them. I've noted it out.
Okay. Thank you.
Okay, thanks. So this S and S will get cancelled. Always there is a S, so this will give you 0. Ka equal to 0, where E of S is equal to 1 by Ka. This will give you infinity. As we know that for type 1 system, parabolic input will give you or Ka belongs to parabolic input, so that will give you infinity. So back to back, we are just practicing the table. The third question is, find the error when the input is RAM with the magnitude of 4. 4 by s square instead of 1 by s square. So how we are going to see if the input is RAM, R of s is equal to 4 by s square. So for this, they have asked the error only, right? So we can straight away solve this. E of s is equal to 1 by s plus sg into limit s tends to 0. I have forgot to put this. And this will be limit s tends to 0, 1 by s into s plus s into 40 s plus 2 by s into s plus. Okay. Oh, this is for unit input, right? We cannot use this right away. Right. I will take the original equation and write E of s is equal to limit s tends to 0, s into 4 by s square divided by 1 plus 40 s plus 2 divided by s into s plus 1 into s plus 2. Now this s and this s will get cancelled. Limit s tends to 0, 4 by some s term will come. So since this s term will came here, I think this will be infinite. Is it so? No. Okay, let me write it and see. This s I'm writing here itself. So there is a s here. So that will get cancelled. So limit s tends to 0, 4 by s divided by 1. So this whole term s into s plus 1 into s plus 4 plus 40 into s plus 2 whole by s into s plus 1 into s plus 4. S and s will get cancelled. You will be left with 4 by this whole term, sum s term plus 40 into s plus 2 you will get. Since it has s, if I put 0 here, this term will go to 0. And
4 by
This term will 4 by 40 into 2. So this will be
1 by 20.
1 by 20. Right. This way we can call it as E of SS when the input is RAM. Sorry, 4 by SS square. Good. That is answer. Oh, this will not be 10 4 by 20, right? EFSS will be 1 by 20. That's it. The third question is the second order system where we want to use that time response specifications just to make you work on that. We have written those formulas, right? I will take it here. Since I have written it in different PDF, I will use here. First, they have given, just try to solve with me so that you will also get some practice. CFS is equal to 25 by s square plus 6s plus 25 they have given. So whenever they have given this and ask for time response analysis, the first thing you can do is compare it with the standard system. Omega n square divided by s square plus 2 zeta omega n s plus omega n square equal to 25 by the rest of the terms. This will give you omega n square is equal to 25. Easy, it will be easy to compare. Omega n equal to 5. The next term is 2 zeta omega n is equal to 6, where omega n you already know. 5 is equal to 6. This will be 3. Zeta is equal to 3 by 5. Value you will get 0.6. Yeah. So zeta will be 0.6. You know this. Now you have the formula in your hand. Just straight away fit those formulas into this. You will get the answer. First question is find the rise time. TR is equal to pi minus theta divided by omega d, where omega d you know. Sorry.
Omega n.
Yeah, omega n into root of 1 minus zeta square. But pi is equal also you don't
Cos inverse.
should know what is theta.
Cos
Theta will
inverse.
be, oh, this will be tan inverse. You only know the information about the zeta, right? Right? Theta will be equal to tan inverse of this terms. Just use the calculator. I don't have calculator right now, so the answer will be, let me check once my notes. If you calculate this value, you would get root of, this root will be only for the numerator, okay? And this, instead of zeta put 0.6, you will get something like 0.92 radians. Theta will be equal to. So once you get the theta, just plug it in here. You will find the rise time. Pi minus, pi will also be in radians. When you put it in the calculator, consider it as radians or consider both as in degrees. So it should be even. That is the point behind it. Okay, by 4, this will give you some value. What is the value? Around something 0.5. Just cross check with this, okay? I haven't calculated right now. It was pre-calculated. Since it's the time and going to use this unit, don't forget to use this unit if it is a statement.
In right side of PDF, ma'am, theta is also cos inverse of theta.
You can use that also. That will also work. Easy to use this. Yeah. When you are using calculator, it will be easy to use. Right. Good. First we found. Second thing is peak time. So the peak time would be, here is the formula, pi by omega n root of, where you have calculated this. Oh, we haven't calculated this before. Just fit in that omega n, what you have found, 5, right? So 5 into root of 1 minus 0.6 square. Answer will be, if you solve this, you will get this answer. The third question is peak overshoot. Will be in MP percentage. So for that, the formulas here in the right hand side, MP is equal to 100 into, since it is a percentage, we are multiplying it with 100 e power. Just don't forget about this negative sign, okay? Zeta pi divided by root of 1 minus zeta square percentage, 100 into e power minus of 0.6 pi by root of 1 minus 0.6 square. This is whole e power into percent. If you solve this, you will also get some percentage that is nearby 9.4 or something. I'm not sure. Just cross check with the answer. Fourth one is the settling time, that is TS. Where is settling time? When it comes to settling time, there will be the percentage in the question. Usually you will be asked to find either 2% tolerance or 3% tolerance. Since it is not in the question, since it is a practice question, you can find, 5%. You can find both of that. Just find the settling time for both. Zeta is 0.6 into 5, and for 2% it's equal to 3 by 0.6 into 5. It's for 5% tolerance, right? This question is expression for its output response when subjected to the unit step input. They have asked. Okay. First, output response, how the output response will be for a unit step. Then we'll just straight away want to calculate it for 1 by s. So since they have asked in terms of, we are going to consider it in terms of t, I think it will also be mentioned somewhere too. The formula for that. I couldn't find formula. Just the output response they have asked.
Ma'am, output response is just input times the transfer function in Laplace domain.
That is fine, but since it was not asked in, there is no answer here, right? There is no option here. So I'm thinking how the answer should be in terms of what time domain or Laplace domain. Laplace domain is also correct. That will be easy to solve.
They say unit ramp input, unit step.
But actually, the question is not clear. The question should be what is the output response in terms of time domain, C of t, if it is asked. If it is in terms of C of s, or y of s, you can straight away use that equation, r of s divided by 1 plus g of s into r of s, h of s, that you can use. But here it's little complicated. It was solved in terms of C of t. So I think you should know this answer also. If sometimes in the exam, if they have asked to solve in time response, you would be
We
you
will
would
take
find it
inverse.
difficult. Yeah,
Inverse.
cool. That is right. But there will be a predefined output. I couldn't find it. See, here it was mentioned the step response for second order system. They have given this. No. So similarly, you should use some. You can use this formula also. Just wanted to let you know that. Give me a minute. I think it is not mentioned here. It might be taken from the book. Just you can follow this. This is a second order system for step response, right? You can either use this equation, which will step response of the second order systems is under damp. What is the damping of us? Zeta is equal to 0.6, right? So you should look for under damped case. Okay. So you should use this formula to find the either you can follow taking the Laplace, finding the output response and taking the inverse Laplace transform, and this is another way to solve the problem. Just use this formula. It's little complicated, I know, but if you have this values of omega d and zeta, you would be able to find this in the calculator use, right? Just look for that particular case with your zeta value. When zeta comes under the underdamped case, just use this formula to find the output response y of t. When it comes under undamped case, just try to use this. So similarly, based on your zeta value, you would choose the output response of this. This is one way to solve this problem. That's it. Since you are using the time response information. When you find all these things and if you know the transfer function, since you know the other way around, that taking Laplace and inverse, that will also be helpful. No issues. It's just for practice. Okay. The fourth question is, for a second order system, they have given one system which is square. 2 d square y by dt square plus 4 dy by dt plus 8y is equal to 8x, where y is the output, x is the input. Because when you want to write a transfer function, you should know this. They have asked to find the calculate the damping ratio. So when you want to find the damping ratio, you may want to convert this. Anybody is speaking something? Okay, so they have given in terms of differential equation, right? So if you want to find the zeta, you want to write it in terms of a transfer function. So till week 3 we have been doing this, right? In applying Laplace transform and finding the transfer function, and then you want to apply this step. Just compare it with the standard transfer function and find the zeta. That's it. So if I want to implement Laplace transform for this, since it is a degree of 2, I will write it as 2 into s square into y of s. I'm going to consider all the initial conditions are 0, since it is not given in the question. So minus 0 plus 4 into s into y of s plus 8 into y of s equal to 8 into x of s. Now this y of s, if I take common, 2s square plus 4s plus 8 will be equal to 8 into x of s, where y of s by x of s will give us 8 by 2s square plus 4s plus 8. But see if it is in terms of the standard equation. It is not, right? There is one coefficient here, so you have to get rid of it. So if I take 2 as a common, this will be 4 by s square plus 2s plus 4. Now whether it is in the standard format? Yes, because this is omega n square and omega n square are constant. So omega n square is equal to 4 will give omega n equal to 4. 2 zeta omega n equal to 2. This will give us 2 zeta into 4 equal to 2 get cancel. Zeta is equal to 1 by 4, 0.25 is the answer.
Yes, ma'am.
Right, good. So this is we have solved this practice assignment, and the final question one is there. A second order system has poles at s is equal to minus 1 plus or minus j, 1j. The step response of the system will exhibit a peak value at. So they have given a second order system. So the denominator will have two poles, s square something will have. So two poles. Somebody raised your hand or
Ma'am, omega n square was 4, so won't omega n be 2?
oh sorry. Yeah. Omega n will be 2. So this will be 1 by 2, then it is 0.5. Thank you for pointing out. Okay. So coming to the fifth question, s is equal to minus 1 plus or minus j, right? So they have told that it's kind of riddle where it is a second order system they say, and there are poles, location of poles they have given, where it will be minus 1 plus j somewhere here, four pole pairs. Okay. So then they are asking for step response of the system. When this if I give a step input, the answer behind this is the step response of the system will exhibit peak. This means if I give a step input to the system, when will the peak will appear, or what is the time of the peak, where the peak will appear? This is the question. So indirectly you are asked to find the TP, right, where the input is given as step. Good. They haven't given anything about the magnitude of the step, so I'm going to assume it as unit step. Right? Since the poles they have given s minus 1 plus j, it's one pole, another pole will be s minus 1 minus j, will be the another. So this will give you, if I straight away compare it with the standard transfer function, s square plus 2 zeta omega n s plus omega m square, as a characteristic equation, I'm going to find the equate this both of this system towards this. So this will be s square plus 2 zeta omega ns plus omega n square will be equal to s minus 1 plus j into s minus 1 minus j. Right? Now, there is a straightaway formula to find this. If you solve this, you can see the s will be equal to, since it is a pole pair, you can straight away use this, that is s is equal to minus zeta omega n plus or minus j into omega d. Right, comparing this with s is equal to minus 1 plus or minus j, you will have zeta omega n will be equal to 1. Already there is minus 1, right? So this will be equal to 1. Then omega d will be equal to 1. So just straight away compare these two equations. So this will give you omega d, we know root of 1 minus zeta square is equal to 1, where zeta omega n is equal to 1. So if I multiply it with inside, how can I solve this? Can I put omega n is equal to 1 by zeta and put it here, 1 by zeta into 1 minus zeta square equal to 1. So this will give me root of 1 minus zeta square equal to zeta. Let me know if I do any mistakes, okay? 1 minus zeta square equal to zeta square. So you give you 1 minus 2 zeta square equal to 0 minus 2 zeta square equal to minus 1 zeta square is equal to 1 by 2, zeta is equal to 1 by root. Good. Now we found zeta. Once we found zeta value, we can find omega n. This will be root 2. Just we know these two. Find the peak time. I forgot the formula.
Pi by omega d.
Good. Okay. Just pi by omega n into root of 1 minus zeta square. Just put the value for this, you will get the peak time something around 3.1 seconds. Good. These are some of the problems that concentrate more on the steady state value, finding the steady state errors for different kinds of inputs, and the time response analysis of any system. First, you have to go through the table just consider what are all the type of the system. When the type of the system is this, giving these kind of inputs, how the outputs will be. Just go through that and once by yourself, and then be aware of the formulas for the time response analysis of the system. You will be able to solve most of the questions from week 4. One or two questions from this kind of then and there, what we not practice, like this output response, finding this output response. That also some of the concepts like using the Laplace and inverse Laplace transform, you will be able to manage. You won't be stuck anywhere. Like, if you have any doubts, just ask me. Otherwise, you can try. I
Ma'am,
will.
what is syllabus for quiz 1?
What is that?
Syllabus for quiz 1.
Till week 4 content, including week 4 content. The questions will be objective questions, which might include MCQs, MSQs, and short answers, where you will be able to solve it using the calculator given in that in the computer-based exam portal itself, and need some formulas to remember and some concept to remember. That's it. Just go through the properties of Laplace transform. Some of the important concepts I have given in the week last Friday, I think. So some of them I remember is just practice the convolution, Laplace transforms, properties of Laplace transforms. What else? This time response and some frequency response questions, basics, and steady state errors. What else? This open loop, closed loop, transfer function. Transfer function properties. What else? I couldn't remember. Some mechanical system, rotational systems, and how to write a transfer function for any systems. That's it, I guess. How to write a mathematical model for any system. It's from the week 1 content only. Just if I give only one block, mass block, or some spring block, and some mechanical diagram if I give, you should be able to write the mathematical equation. So it's one kind of problem you could expect. Similarly, electrical systems, mechanical systems, rotational systems, just go through that. And some of the standard examples we have given in week 1, just go through all those things, simple pendulum, models. And pretty much you will be able to cover with this. Anything else? I will upload this notes in the link. I will give the link for this. And within quiz 1, we will try to upload what are all the live sessions we have recorded so far. Some of the live sessions we couldn't record due to some issues. That won't be there, but most of the sessions will be there.
Can you share any previous year question paper?
Previous year questions I don't have. But using this live sessions, graded assignments, and actual assignment solutions you would get, right? Answers you would get. And you could discuss it with us. If you have any doubt, you can come to the live session. We will have 2-3 live sessions before quiz. Just start to practice those assignments from now. Whenever you have doubt, just note it down. You can ask in the discussion forum also. Otherwise, in the live session, you ask those questions, we will discuss. If you cover this graded and assignments, graded assignment, practice assignment, and some of the contents from each and every week, you will be able to perform better. Maybe able to score more than 95%.
Yes, ma'am.
This is enough actually. Good. If you have any other doubt,
No, ma'am.
okay. Then thank you for joining.
Thank you.
Thank you.
Thank you.